Last lesson, you learned how to use the SSS and SAS postulates to write flow proofs showing that two triangles are congruent. Today, you are going to learn two more postulates that prove triangles congruent, ASA and AAS. Now go to your postulate paper, find the angle side angle postulate, and add these two diagrams. The angle side angle, or ASA, postulate says that if two angles and the included side between them are congruent to two angles and the included side of another triangle, then the triangles are congruent. You see this pattern of matching angles, matching sides, matching angles. You do not need to check the other two sides or the other angle. You could assume that they will match as well. Next postulate, add this diagram to your postulate paper. The angle side postulate, or AAS, says that if two angles and a non-included side of one triangle are congruent to two angles and a non-included side of another triangle, then the two triangles are congruent. Add these two diagrams to your AAS box. Now, here's the confusing bit for a lot of people. When you compare this theorem with the one before, ASA, both postulates are saying that if you have two pairs of matching angles and one pair of matching sides, that's enough to prove your triangles are congruent. There's a very subtle difference between them, and that's where the pair of matching sides are on the triangle in relation to the pairs of matching angles. You use ASA if your pair of matching sides is between the matching angles. That's why S is between the A's in the name. You use AAS whenever the pair of matching sides is not between the pairs of matching angles. That's what non-included means. Included is a fancy word in math for between. Non-included means not between. All right, so your job is to look at this diagram. It's not on your notes or on your postulate paper, it's just on the screen. And your job is to decide which of the four postulates you've learned so far is being demonstrated here. To prove these two triangles congruent, would you use SSS, SAS, ASA, or AAS? Have you put A's by the congruent angle symbols and S's by the congruent side symbols? You see it's two pairs of matching angles with one pair of matching sides between them, so it'd be ASA. Notice how the pair of matching sides is between the matching angles, so the S is between the A's, not at the end. It's ASA, not AAS in this particular case. Just like the last lesson, you'll find that the easiest way to write proofs today is going to be the flow proof format, because generally speaking, you need three bubbles representing your three congruent sides or angle pairs, pointing to one bubble saying your triangles are congruent, and sometimes extra bubbles to build up to your three main ones. Now, when you read the given, it's telling us that segment BA or side BA is congruent to segment EA, so you can add that to the diagram if it's not already there. Sometimes the given is on the diagram, sometimes you have to add it yourself. The given also tells us that angle B and E are right angles. Now, we want to make sure that we reserve our three main boxes for equations about equal sides or angles. So if it has a congruency, that works. So the part of the given that says we have a pair of matching sides, that can go in one of your three main boxes. However, the other part of your given isn't an equation, though it might help us figure out an equation about sides or angles later. So you're going to put that in the little prefix box, because you'll use that to create an equation about sides or angles, but it's not telling us we have two equal sides or angles quite yet. So we've broken up the given and put it in the right bubbles. Next, we want to look at the diagram and see if there's any pairs of sides or angles that just looking at the diagram we know have to match. Here's a good rule of thumb if you want to jot down this note to yourself on the side. The types of congruencies you can figure out from the diagram generally boil down to either vertical angles or shared sides. So if there's a side that's between your two triangles, that's a side for both the triangles. You could use reflexive property and use that for another pair of sides. If you have two lines crisscrossing and making an X, you know opposite sides of an X are equal because vertical angles are always equal to each other. So if you look for shared sides of vertical angles, that usually helps you figure out more congruencies between your two triangles. In this case, our triangles do not share a side, so that's ruled out. However, we do have two lines crossing. We have an X, and we know opposite sides of an X are equal because they are vertical angles. Now, notice how both of these angles, like we could call them corner A on both triangles. It's corner A on the left triangle and it's corner A on the right triangle. That would be awfully confusing though, for two angles to have the same name. Whenever you have two angles that start at the same vertex point, you have to use the three-letter version of an angle name instead of the one-letter version of the angle name. So we cannot just say angle A is congruent to angle A, because angle A is referring to two different angles then. But you could call it angle CAB equals angle DAE. The important thing is the vertex is in the middle of the name. A has to be in the middle of the name. Your official reason would be vertical angles theorem. That's one you'll use quite a bit when you see a diagram like this in chapter 4. So at this point, we have two equations about matching sides or angles. We need one more, and it somehow has to build off of that part of the given we haven't really used yet. Now, if angles B and E are both right angles, that means they're both 90 degrees. In other words, B and E are equal angles, so angle B is congruent to angle E. Your official reason for writing that is actually an old chapter 2 theorem. If you go way back to chapter 2, when you learned about things like vertical angles and so on, one of the theorems you learned was Theorem 2-4. Theorem 2-4 is one you haven't used much yet, but it's one that says anytime you have two right angles, they are automatically equal to each other. It is one of those theorems that when we learned it, it didn't seem like it would have much use because it was kind of stating the obvious. Of course, if two angles are 90 degrees, they equal each other. But now that you're in chapter 4, it's a very useful theorem because it works as an official reason for saying things like angle B is congruent to angle E. Now, let's look at your diagram. If you haven't added congruent angle marks to show that your vertical angles match yet, make sure you do that now. Look at one triangle, either the left one or the right one, and label A's on the angles and S's on the sides. Because now that we're copying the proof down here, now that we're officially saying the triangles are congruent, we need to figure out which reason we would use, SSS, SAS, ASA, or AAS. If you said ASA, well done, because if you label your A's on the angles that match, S's on the sides that match, it's an angle side angle pattern. The side is between the pairs of matching angles. Let's take a look at the next proof. In the given, we have one congruency fact given to us for free, that angle S is congruent to angle Q. Mark that on the diagram if it's not already there. The second half of the given, though, isn't an equation about equal sides or angles yet, so that's going to kind of go in a before box. We'll use it to make an equation later. Next, think back to that note you wrote by the first proof. The two things that you could generally figure out from a diagram is whether they have shared sides or vertical angles, and that can generally help you figure out one more congruency fact. Do you see vertical angles? Do you see shared sides? In this particular diagram, there are no vertical angles, there are no crisscrossing lines making an X, but there is a shared side. PR is a side for both left triangle and the right triangle. So that can count as another side congruency fact. What reason would you write? If you said reflexive property, well done. You use that anytime you say something equals itself. We need one more pair of equal sides or angles to prove our triangles match. And somehow our last equation about equal sides or angles is going to be based off of this idea that segment RP bisects angle SRQ from the given. A good rule of thumb when you see a word like bisect or midpoint or anything like that is go find the thing that's being cut into equal halves on your diagram, in this case angle SRQ, and highlight it. Highlight at angle SRQ. So that V at R is what is being cut by equal halves by segment RP. So if you cut the angle into equal halves, you could say that each half angle equals the other half angle. You could say angle SRP has to equal angle PRQ. What would your reason for that be? Definition of bisect. We saw the word bisect. It told us that the angle was being cut into equal halves. So the reason we could make that equation was definition of what bisect is as a word. All right, so at this point we have three congruency facts, three equations about equal sides or angles. So we can go ahead and say we're ready to say the triangles match. Copy the proof. Now we need a reason, SSS, SAS, ASA, or AAS. Look at one of your triangles and label the S's or A's. It should look like that. Now decide which theorem you would use to prove the triangles match. If you said AAS, well done. Now notice how it's AAS, not ASA this time, because a side symbol was not between the matching angle symbols. So it would not be ASA. It's AAS anytime the side is not included between the matching congruent angles. Last one. If you have an equation or a congruency in the given, that can go in one of your three main boxes. If you have any other type of fact in the given, you'll put that before a main box so you can use it to create an equation later. Take a moment to look for vertical angles or shared sides to get another congruency fact. If you noticed your triangles shared side AC, well done. What reason would you use? Reflexive property. Don't forget that when you figure something out, you add a congruency symbol to your diagram because that will help you when you hit the last step. Now, remember on the last problem we talked about how whenever you see a word like bisect or midpoint in the given, you want to go highlight what is being bisected or being cut into equal halves. So go highlight angle BAD. So that's the angle that's being cut into equal halves. So you could add congruent angle symbols to those equal halves and say that angle BAC has to match angle DAC. Notice how we can't just say angle A equals angle A because that's two different angles that would then have the same name. That would be confusing. So you have to use a three-letter version of the angle names. What would your reason be? Definition of bisect. Now we have three equations about equal sides and angles. We can officially prove the triangle is congruent. What reason would you use for that? Once you add angle and side symbols, if you said ASA, well done.